Today, I've got a story for you. It's a real-world developer mystery, a cautionary tale about how all that modern, shiny, async await code we love to write can bring a massive system to its knees in a way you would never, ever expect.
Yeah, you heard that right. This is a direct quote from the engineering team that actually lived through this. It's not an exaggeration. And it's the perfect place for us to start.
All right, so picture this, a brand new real-time notification service for a financial platform. We're talking state-of-the-art. It's built with all the modern goodies, asyncs await everywhere, promise-based everything. And in testing, it was a beast, flawless. Handled thousands of events a second without even breaking a sweat.
But the second it hit real production traffic, bam, total meltdown. WebSocket connections just started timing out. Notifications were sent, but never arrived. Health checks started failing over and over, so the system just kept killing and restarting the instances in a hopeless loop. It was so bad they had to pull the plug and roll it all back immediately.
So now the investigation begins. The team is under huge pressure, and absolutely nothing makes sense. They do what we all do. They start running down the usual checklist of what could possibly be going wrong.
And the first, most obvious suspect is always the CPU, right? Is there some rogue piece of code just spinning away, blocking the whole system and pinning the processor at 100%?
And right away, we get our first clue that something very, very weird is going on. The CPU was fine, totally normal, just humming along at a healthy 45%. So this wasn't your classic CPU-bound bottleneck, not even close.
Okay, so if it's not the CPU, what's next on the list? You check for memory leaks. Is the application just gobbling up all the RAM? Or maybe it's spitting out a bunch of errors that are getting lost somewhere. So you check the logs.
And nothing. Another dead end. Memory usage was rock solid, and the logs were completely silent. From every standard metric, the application looked perfectly healthy. This is where the mystery really starts to get deep.
So this is the paradox the team was staring at. The system was alive, but it wasn't working. You could see JavaScript code was executing, the gears inside were definitely turning, but anything that needed to talk to the outside world, a database query, a network ping, even a simple timer was just stuck, completely frozen. The team was stumped. I mean, all the usual dashboards were green. But then they dug into one metric that's often overlooked, and that one number cracked the entire case wide open.
And there it was, the smoking gun. Event loop lag. Now this number basically measures how long a task has to wait before it gets to run. It should be tiny, like milliseconds. Instead, it was pinned at a constant 8 seconds. That's an eternity. It meant the heart of Node.js, the event loop itself, was spinning like crazy, but it was completely stuck, never getting around to processing any new work.
With that one critical clue, the team finally knew what they were dealing with, and it wasn't some simple bug they could fix with a quick patch. It was a deep, fundamental flaw in how they designed their async code.
The villain of our story finally has a name, Microtask Starvation. It sounds super technical, I know, but the idea behind it is fascinating, and it's something every single developer using async/await needs to understand.
So what on earth is microtask starvation? Well, it's basically when the event loop gets trapped in a vicious cycle. It gets so busy processing this endless stream of high-priority things called microtasks, which is exactly what promise resolutions from async await are, that it never ever gets a chance to handle the lower priority macrotasks. And those macrotasks, that's all your important stuff like I/O, network requests, and timers.
So how does this actually happen? I mean, how can a bunch of tiny, fast-running tasks completely hijack an entire system? Let's dive into the mechanics.
To really get this, you have to know that Node.js has two different waiting lines, or queues, for tasks. You've got the VIP line, the microtasks. These are things like your promise callbacks from async await. They're handled directly by the V8 engine, and they have absolute top priority. The rule is simple and brutal. The microtask queue must be completely empty before the event loop is allowed to do anything else. Then you have the regular line, the macrotasks. This is your I/O, your timers. The event loop only gets to check on this line after the VIP line is totally clear.
And this is exactly how the death spiral started. An event would come in and it would kick off a function that recursively created over 50 promises. So the event loop starts frantically working through that list. But here's the killer. Before it can finish, another event comes in from the outside world and dumps 50 more promises into the queue.
The VIP line just keeps getting longer and longer, it never empties, and all your I/O callbacks, your database results, they're just sitting in the other line, waiting for a turn that never, ever comes.
This quote just nails it. The developers wrote code that looked perfectly correct and non-blocking. They assumed that every time they used await, they were politely handing control back to the event loop to let it do other things. But in reality, all they were doing was adding another urgent task to that high-priority VIP list, effectively monopolizing the system and blocking everything else.
Okay, we've seen the disaster, we understand the mechanics, now for the most important part. How do we avoid falling into this exact same trap ourselves?
The key, really, is to have the right mental model. You have to think about the kind of work you're doing. If something is high urgency but doesn't happen very often, a single quick task, then sure, a microtask like a promise is perfect. But if you have a ton of work, a high volume of tasks, you need to use a macrotask like setImmediate. This intentionally puts the work in the regular line, which ensures the scheduler stays fair and prevents this kind of starvation.
So the fixes weren't just about changing a line of code here or there. It was a real shift in design. It meant getting rid of that recursive algorithm and making it iterative. It meant batching up that high-volume work instead of creating a promise for every single tiny thing. And, most critically, it meant using tools like setImmediate to deliberately schedule work as a macro task, to explicitly tell the system, hey, after you process this batch, go check on your other chores, so that I/O finally gets its turn to run.
And this, right here, is the single biggest lesson from this whole story. Just because you sprinkle the word async everywhere doesn't magically guarantee performance or scalability. It's not magic. It is a tool for scheduling work, and if you don't understand how that scheduler works, what its priorities are, you can accidentally schedule your way right into a complete system meltdown.
So, I'll leave you with this question to take back to your own projects. That async function you wrote, the one that works perfectly fine on your laptop, what happens when it gets slammed with real-world, production-level traffic? Is it truly being a good citizen and yielding control? Or is it just quietly waiting for the right conditions to starve everything else to death?